And I'll give a bit of an introduction about alternative ways that things could have been done so that you understand what's special about 1553. We'll get into the details of the specification and then discuss implementation issues. These are things that are not mentioned in the specification itself, but over the course of time have become common practice. So it's divided into a number of sessions. The first session is the general background, in which I'll talk very briefly about several different avionics specifications. Airing 429 was developed in the early 80s for civilian aircraft. MIL-STD-1553 was developed at the same time, maybe even a few years earlier. It started in 1978 for military aircraft. The newest standard for military aircraft is Firewire, used on the F-35. And the newest standard in common use on civilian aircraft is AFDX. CAN bus is also used, but AFDX is a larger bus. Anyway, we'll just speak briefly about them to give an idea of what the different options are. The second section will talk about the details of the 1553 spec, centered around the idea of a message. What is it that gets sent? And there are multiple different types of messages, and we'll talk about all of them. Following that, we'll talk about things that are not in the spec, such as how do you prioritize messages? How do you make most efficient use of the throughput available on the bus so that the messages that are time critical happen more often and the ones that are less time critical happen less often, all of which is necessary to maximize throughput. Then we'll talk about some of the hardware issues surrounding 1553, including both the hardware used and what the signal looks like. Because for various debug purposes, that can be very helpful. And then we can talk about some applications that Excalibur has developed. The first four sessions really have pretty much nothing to do with Excalibur. They're about 1553 itself. But the fifth session, because software is always going to be company specific, will be about the software that we provide. Okay, so let's immediately move into the introduction to avionics buses. And to start with, we'll talk about who are the clients that need a bus. Why do we need the purpose of a bus is for various boxes on an aircraft to talk to each other. So let's talk about what kind of boxes these might be. So one example is, and in 1553 we call these boxes remote terminals. For example, in AFDX they're called end systems. There are different names for in each spec, but in fact what they are users. So an altimeter measures altitude, and there are many ways that an altimeter can measure altitude. It can be done through GPS or INS or air pressure. And for our purposes, because we're discussing the communication aspect, we don't really care how it is that we came up with the data. That's what altimeter people do for a living. What we do for a living is help them communicate. So you can think of an altimeter as having two parts to it: the part that figures out the altitude and the part that gives this data over to somebody else. So because it's giving data over, I call it an active device. A display is exactly the reverse. A display usually doesn't have very much to tell people, but it gets data from other boxes and displays it. So it's passive in terms of communications. The data is flowing towards the display. A black box similarly is passive. It gets data and records it. And a flight computer would be an example of something that does both. It'll get data from some boxes and send them to others. So these are the types of clients that you might see on a military bus or on an avionics bus, really. Okay, so now in the old days, when there 50 years ago, say you had small planes for the most part, and the altimeter's purpose in life was to let the pilot know what the altitude was. That's all it needed to do. And in that case, a gauge would be the best way of doing that. You would just stick an altimeter of the sort in the picture, and the pilot would look at it. A speedometer, similar plane car, which everyone is familiar with, is again, there's a gauge that the pilot can see. And a compass is the most refined sort of device in this respect, in which the needle, which is that which figures out which way is north, is also the gauge. So you don't even have the two parts that we talked about before, the part that has the function and the part that does the communication. In the case of a compass, it's all the same. However, at some point, and for many planes this happened in the 80s, in the 80s and in the 90s, and now it's completely commonplace, you would have the same altimeter no longer needed to speak only to the pilot. It wasn't only the pilot that cared what the altitude was. The pilot did care, and therefore you would need some kind of a display. But there was also an autopilot. The autopilot needed to know the altitude as well, and a display is not useful to an autopilot. A flight recorder also needs to know it. So once you've got a single device that has to go to multiple places, then you're not talking about a gauge anymore. And in fact, you really want to be talking about some kind of a bus. You're talking about now more likely to be digital data in order to go to multiple places. And you want it to be efficient. So you want it to go at the same time to all the different places. In the case of an engine, just as another example of a box on an aircraft, it'll go to the same three as the altimeter. It might also go to a maintenance slot, right? At some point, every week, every month, you've got to figure out how many hours it worked, how hot it got, in order to determine what kind of maintenance you have to do for it. So that's the now examples of new kinds of data that we're going to have to transmit. So let's have a look at how we might wire such a thing. So the simplest method of wiring is just take a wire, start at the altimeter, and then send one wire to the display, another wire to the autopilot, a third wire to the flight recorder. And similarly with the engine, this time you'll need 4 wires. And in fact, this wiring diagram very closely simulates what ARINC 429 does in a civilian aircraft. And it works perfectly well. It's certainly very straightforward. But it has a number of disadvantages, as we'll see. Now let's take a military application. This is what they were thinking of when they developed MIL-STD-1553, where obviously all the same things you need to run a civilian plane, you kind of need to run a military aircraft. Well, maybe not all of them. Civilian planes have smoke detectors in the bathrooms. I don't think they need those on fighter planes. But in any event, you do, in addition to those things, you also need other things, such as, for example, missiles might be on a fighter plane. And each missile needs to be connected to a whole bunch of different things, right? The pilot has to know whether the missile is working or not. So you need some way for the missile to send data to the pilot. The pilot has to have a way of shooting. So you need a trigger. Before you do that, the pilot would like to check, is everything working properly? So that would be a weapons test button. And presumably you want a flight recorder so that later on you understand exactly what decisions were made and why they were made. Certainly if things go horribly wrong, you want that, but even if they go right, it's not a bad idea. Okay, so now let's take these devices and figure out what the wiring could look like. So if we use the same wiring as we just discussed is used in ARINC 429, this is what it would look like. And if you have, instead of 4 missiles, 10 missiles or 20 missiles, then it would obviously look considerably more complex. And this causes all kinds of problems. First of all, it's heavy. Wire is heavy. And weight is very much at a premium, because the more weight you've got on the aircraft, the more powerful the engine has to be, the more gas it's going to take, and therefore the less weight you have available for your missiles or for your pilots. So weight is one key downside of having such a huge number of wires. The second thing is that every wire you have can potentially break. And the more wires you have, the more likely it is that one of them will break. And all the soldering points As here, connected to missile 1, we've got 4 different wires. So let's get a pen color here, orange. Okay, so right at this point, you've got 4 solder points, and you've got the same 4 solder points for each missile, and in this case, 4 solder points for each of the. Every solder point is a weak point, and could potentially cause trouble. Okay, so in cases like this, where you're going to have too many wires and too many soldering points, what you want is a digital bus. And this is an example of a digital bus. The bus itself is this wired, the vertical wire here. Now, attached to this, you've got a whole bunch of what we might call stubs. So this is going from the missile, attaching to the bus is a stub. Similarly, from this mission computer attaching to the bus that's a shorter stub in the picture. Okay, so what we've got then is one bus, and attached to it are 4 missiles, a display, a trigger, a weapons test, a flight recorder, and we've thrown in something new, a mission computer, which up until now hasn't been in our picture. Okay, so what does this do for us? Well, the main thing it does for us is now you've got a single connection point to the missile. I shouldn't say solder point because it doesn't have to be soldered. In fact, in 1553, we tend to use twin X connectors. So you've got one connection to the missile and one connection to the bus for each device. And no matter how many devices you have, you've got the same one connection to the device and one connection to the bus. So you've now decreased your number of connections enormously. You've decreased the weight enormously, and everybody still is able to communicate. Okay, so it weighs a lot less because you've got less wiring. It's easy to install because each new thing that you install only has to be attached in one spot instead of potentially attaching it all over the plane. And because it's easy to install, you can add RTs without too much trouble. Now, when you add an RT, it doesn't, not just the physical issue, right? Obviously, you now have to deal with the RT at the communications level. Somebody has to know that it's there in order to know to talk to it. So right now, when I say easy to add RTs, I'm speaking strictly from the point of view of the wiring. Okay, so now we added this bus controller. Why did we add a bus controller? We had in the previous wiring diagram with the 429, we just directly wired each of the 4 missiles to each of the 4 devices they needed to be attached to. And now that's not sufficient. And then once we have a bus, we now had to add a bus controller. In fact, we didn't have to add a bus controller, but that was a decision made in 1553. But what was the problem that we was trying to solve? Okay, so the real issue is if you have point-to-point communication, when a transmitter has something to transmit, he transmits immediately. As soon as the data is available, he sends it out. But if I've got 8 devices, right, in our case, the 4 missiles and the display and the trigger and whatnot, so I've got 8 devices, any of whom might have something to transmit at any time. Okay, well, if they transmit at the same time and it's only a single wire, then they're going to crash into each other and nobody's going to be able to understand anything. And that brings up the problem of if you now were sharing a wire as opposed to 429 where everybody had their own wire, how do I share a wire and still not allow data to crash into each other? And this is one of the central issues that all networks have to deal with. And the way 1553 deals with it is through the bus controller. The bus controller decides who's going to speak at any given time. Now, there are certain side effects to this. One is since the bus controller has to now speak directly to each of the RTs or terminals or boxes, so it's in direct communication with all of them. And in 1552, they said, all right, as long as I'm in direct communication, let the data always flow through the bus controller. So the bus controller would send data to each of the RTs, and it will get data, receive data from each of the RTs. And as a side effect of this, the fact that it's speaking directly to all of them, if there's a problem with communication, wire got cut, there are parity errors, too much noise, all of these things the bus controller is going to know about immediately because it's the one who's involved in every communication. So that's actually a very positive note. Okay, so now let's talk about the pluses and minuses. We'll start with the minuses. And the first minus is that by virtue of the fact that we've reduced 16 wires down to 1, you've also got a single point of error for every single device on the bus, right? And if the devices on the bus are things like radar, engine, landing gear, you really don't want to lose communication with those things, right? Because the plane's going down. And therefore, 1553 always has redundancy in it. Now, redundancy, right now I'm talking redundancy at the communication level. So there's no such thing as only one wire, and we'll see what this looks like physically later on. But the idea is that every box has 2 wires coming out of it. We'll call them bus A and bus B, and they work in parallel, so that if something goes wrong with bus A for whatever reason, we still have bus B available. Now, another difficulty with the 1553 as opposed to the direct wiring method is that all the data of all the devices have to flow on the same bus and they have to take turns. Whereas if we have parallel wires, then they can all transmit simultaneously, which means that the throughput is considerably reduced. The amount that any single box can transmit is no longer 100% of the time, but if you got 30 boxes, it should average down to about 3% of the time. So you're losing a lot there. And in fact, 1553 and 429 were developed at roughly the same time, and 429 had 2 major speeds. The higher speed was 100 kilohertz, meaning 10 microseconds per bit. Whereas 1553, understanding that they had to make up for a lot of inefficiencies in terms of transmission, immediately made their speed 10 times that. So it's a megahertz or a microsecond per bit. Now, today, obviously, these are considered extremely slow data rates, but when it was developed, it was sufficiently fast. And for the kind of data that goes on most of the time on a military plane, it's fine. For example, altitude data, you really don't need to have it, in a microsecond. The altitude's not changing that fast, and if it is, the pilot will know. Okay, and then in addition to the fact that it's serial, there's a lot of extra overhead on a bus, right? Anything that the bus controller says, since there is no bus controller on other types of buses, so all of the bus controller transmissions are overhead, which you don't have in others. So in order to deal with that, we have this notion of minor frames, which is an efficiency issue, which we're going to get to in the timing section of the course. And lastly, if in addition to any of the cables potentially being problematic, for which we already said we have dual redundant buses, if the BC itself doesn't work, then again, the plane goes down. I may be exaggerating, but I may not be. There typically are multiple buses on a plane, and so one of them will probably have to do with armaments. If that one goes down, then it won't cause the plane to crash directly, although if somebody is firing at you, then it could potentially cause trouble. But if you're talking about the bus that's in charge of navigation, you really want to know where you are and where those mountains are. And if you don't, that could be very bad. There's an example of very bad. Okay, so now to give you an idea of other possibilities. So we saw 429 was just direct wiring. And now, and 1553 was a single wire that all the devices are connected to. And here we have Firewire, which is originally developed by Apple for video equipment, and is currently used on the F-35 fighter, and I mean with minor modifications. And it uses a totally different method. It uses a binary tree configuration, so that if you look at the picture on the bottom, actually the numbers are, we have, well, no matter. Let's say you want to communicate between node 5 and node 11, right? So the way you communicate is you go up to node 6 and then down to node 11, right? Whereas if you want to communicate between 5 and 4, then you'll go from 5 down to 9 and down to 4. So here, unlike the 1553 bus, if these two things wanted to happen simultaneously, they could, because they're independent wires. In addition, you see there's no bus controller. So they had to deal with the problem of how do you get things not to crash into each other. So one method is if they happen to be using paths that don't intersect, then they won't, then that won't happen. However, let's say, you know, number 6 here wanted to talk to number 9, and number 7 wanted to talk to number 5. So then there's a lot of overlap here. 7 will talk to 5 that way, and 6 will talk to 9 that way, and there's going to be overlap. So how do you prevent that? So there are two basic methods. One is that each one of these nodes itself only will send one message at a time. So that if let's say 6 sends something to 7, and 7 has its own message to send to 2, 7 is going to can decide which one to send. But in fact, what Firewire uses is a more complex mechanism having to do with timers, and it sends out a timing message to the entire bus periodically, and everybody has their own time slot that they're allowed to transmit. So that's the method that they use to make sure that you don't have multiple transmitters simultaneously. So it's a little bit more robust than 1553 because of the multiple paths, and it doesn't require a bus controller, which means that that's one less single point of failure, but it's really complicated. And the hardware and the software, there's a lot of very specialty stuff going on over there, which makes it complicated, and complicated translates into expensive. Here's another example of a bus, the AFDX, which is currently used on the Airbus 380, probably a few others, and Boeing also is, if they're not already using it, they're certainly planning to use it. It's basically Ethernet. A few years back, actually about 20 years back, Airbus and Boeing both decided that they deserve their own bus. They're like two of the biggest companies in the world, and why shouldn't there be a special avionics bus? They made one, and they called it A-Ring 629, and it was custom to exactly what they needed. But what they didn't figure on is that as big and important as they are, there were not thousands of people ready to start working with this incredibly complicated bus. And as a result, a lot of the parts that were built were single source. Single source translates again into very, very expensive. The whole thing just crashed and burned. So they decided now, when they were going to the next generation of civilian bus, that this time they would be a bit more modest, and instead of creating something from scratch, they would say, all right, let's look at what's out there and how can we make use of it. Well, there's nothing more out there than Ethernet, right? Pretty much every person on the planet, well, okay, let's say 2/3 of the people on the planet have Ethernet, and there's just a huge amount of activity done on improving it, and it gets improved all the time. So now they said, all right, that's the starting point, but it's not really designed for airplanes. And as 2/3 of the people on the planet know, it doesn't always work, and doesn't always work quickly. And that's not the sort of thing you really want when you're controlling an aircraft. So first thing they did was add dual redundancy, right? You don't want to have one wire, as we saw before. You don't want to have a single point of failure on an aircraft. So there's always dual redundancy on A-Ring 664. The other thing that they said was, well, one of the reasons that people tend to lose data on the internet is because there are so many different ways that data can get from one place to another. Right? When I want to read a newspaper, I will open my browser and put in the name of the newspaper, and then it'll go from my browser to my switch, or my hub more correctly, and then from my hub to the office switch, and then from the office switch to the phone company, and from the phone company to the undersea cable area, and from there to the other side of the undersea cable, and from there onwards and onwards. There's a lot of, and there are actually, could be 50 undersea cables. And, so there's a huge number of possible paths. And each one of those possible paths goes through different hardware, and some of that hardware is going to work better than others. So you've got a mess. You don't need that on an airplane. Airplanes are relatively small relative to the planet, and you can figure out exactly how everything can get to the place it has to get with a single path. Now you want redundancy in the path, but a single path. Other things that the AFDX will differ in than say 1553 is the size of a packet, right? And Ethernet allows, roughly speaking, 1500 byte packets, whereas as we'll see, 1553 only allows 32 16-bit words per packet. Now, let's see. You also have the ability to detect if data has been lost. This is something that parts of Ethernet have more than others, but they insisted on having it for them. On the downside, there's high overhead, right? You've got Ethernet has a 42 byte, packets header for the data. If you only got 2 bytes of data, you got 42 bytes of overhead and 2 bytes of actual data, which is not that efficient. So AFDX will be most useful for large amounts of data. And in fact, that's pretty much the way it's used. Okay, so in summary, if we look at ARINC 429, 1553, Firewire, and AFDX, so direct lines are simple and cheap in terms of, since they're less complex, there's not much of there's no software overhead, there's no bus controller. They can become expensive because of the weight that they represent. But just in terms of the design of the system, they're very, very straightforward. On the other hand, they're only useful if you've got only one transmitter on the bus. If you've got multiple transmitters who need to speak to multiple receivers, then a bus is much more appropriate than a direct wire. And buses are much simpler in terms of the hardware, in the sense you can have one wire instead of 50, but they're much more complicated in terms of the methods that you have to use to make sure that the data doesn't crash into each other and things like that. So each has their own use. ARINC 429 is direct line, 1553 and all the others, in fact, they're buses, and there are good reasons for that. Okay, so that takes care of the general introduction to avionics buses. Now we're going to go into more detail of 1553 itself, and we'll start with what the goals were, what are the design goals, and then talk about the mindset. Now, I don't talk about the mindset in any of the other bus courses that I give, but in 1553 it's quite important. And then message types, which is the key to understanding the communication. And we'll talk a little about MIL Standard 1760, which is a subset of 1553. Well, and it just adds a few requirements. Okay, so the goals, the design goal were communication between up to 32 boxes, right? You're talking late 70s, airplanes, F-15 probably was already around, if not certainly the earlier Fs. So not very large planes that don't have tons and tons of things on them. 32 boxes seemed like the height of what anybody might ever want to use. On the other hand, the amount of data each of the boxes also not very great. Data we're talking about are things like altitude, latitude, longitude, various discretes, as in statuses and triggers and things like that. So they needed, so that was the order of magnitude of what the bus had to handle. And they were very, very keen on the idea of high reliability. And high reliability requires you to know when there are errors and to be able to retry if there's an error, right? Because communications are not perfect. So if you don't get something, you want to know, right? If you know, then that's fine. Then if it's critical, then resend it. And if it's not critical, then at least you know. Okay, so mindset is very much a military mindset, which is why we have this notion of a bus controller, which you don't see in any other bus. And the idea in a military mindset is there's somebody in charge. And that's how you make sure that nobody messes up. The commander is in charge. He decides who does what and when they do it. Nobody speaks before the commander tells them to. And when he talks, he either tells them what they need to know or he asks them what he needs to know. But he's the one who makes this determination. He can speak to everybody at once or one at a time. And all of these things are very directly found in 1553. Okay, now the 1553 message is the way data is communicated at any given time. So a message will take somewhere between 20 and about 700 microseconds. And that's what, if you look on the bus, that's what you see. Message followed by message followed by message. Each message might be a different RT. Some of them will data will go to the RT, some will come from the RT, but every single message is initiated by the bus controller. And the first word of every message is the command word. And the command word, therefore, is written by the bus controller. So every message on the bus will start with a command word, which is transmitted by the bus controller. Okay, now here are the various types of messages. The first, the two most common ones are the first and the third lines, where the bus controller sends data to the RTs, or the bus controller requests data from the RTs. Now, the bus controller can also send data to all the RTs simultaneously. We call that a broadcast command. It's not used a great deal because there's not a lot of data that a radar and an engine and landing gear all need in common. So the sort of thing that they might want to have in common is the ability to synchronize. So you can send out a broadcast message to all of them saying, reset your time tags. And in fact, that kind of message is our fourth kind of message we call a housekeeping message, where we're not trying to move data from one box to another, but we're trying to do things that have to do with maintenance of the bus. So synchronizing everybody is one such example. Another example might be a message saying that bus B is very noisy, we're going to stop using it. Either we'll stop using it altogether or a particular RT should stop using it. And we'll see other examples of mode codes. RT to RT commands are less common. I just want to check, right. And they are commands in which the bus controller asks one RT to transmit data directly to another RT. So here the data doesn't have to go through the bus controller. The bus controller sees the data, but the receiving RT sees it simultaneously. And these are less common for also because why would two RTs both know the same data types? Right? Presumably only if they were built by the same manufacturer. Because there aren't really specs determining what RT communication has to look like. The spec, in fact, the 1553 spec doesn't talk at all about what it is you're supposed to communicate. You can think of the spec as being a specification for a telephone in which you don't tell people what to say. Other specs are not like that. 429 actually in the specification tells you exactly what to say. Let's see. Well, some do and some don't actually. So that's various specs handle that. In the OSI network levels, So there are different levels discussed in terms of communications, and the 1553 will be at a low level. It's really describing the hardware more than anything else, and the message type, but not at all the content. Okay, so now these are what the names of the messages are. What do the messages actually look like? So every single message starts, as we said, with a command word. And following the command word, there are two different kinds of other words that can exist. There's the data word and data word or words, and the status word. And we'll look at each of these things separately. All right, we'll start out with the command word, and the command word has 4-bit fields in it. There's the RT address, there's a 5-bit field, transmit receive bit, right? And then follow that by a 5-bit subaddress field and a 5-bit word count field, and that makes up the full 16 bits. Every word in 1553 is a 16-bit word. Okay, so let's talk about these fields one at a time. The first two fields on the left, you have the RT address. Because there are 5 bits, 5 bits gives you potential values from 0 to 31, which is why I said at the beginning that one of the design goals was to be able to connect up to 32 boxes. And this is where that comes into play. That decision of 32 boxes comes into play with the fact that it's a 5-bit field having the RT address. And now this is a way that the bus controller directs the RTs as to who it is that he's talking to. So if the bus controller has data for RT3, these top 5 bits are going to contain a 3. Similarly, if he wants data from RT7, these top 5 bits are going to contain a 7. If he wants to speak to all of them simultaneously, then the system knows that our address 31 is a broadcast message and everybody has to listen to it. And there will not, therefore, be an RT whose own address is 31. On many RTs, there are straps on the RT which lets you set the RT number, right? Because the manufacturer doesn't want to set it because he wants to sell it to a whole bunch of different planes, and each plane may need it to be a different number. So he'll put dip switches or something like that, jumpers, and that the user can determine which RT address he wants. And based on those numbers, they will now pay attention to the upper 5 bits to see if it matches that number. But if there's broadcast, then they'll check if it matches either that number or broadcast, and they'll listen to it either way. The second bit is a bit that says, what kind of a message is this? Is it a BC to RT message or an RT to BC message? The nomenclature for that is, if it's a 1, we call it a transmit, and if it's a 0, we call it a receive, and this is from the point of view of the RT. So transmit means that the data is flowing from the RT to the bus controller, and receive means that it's flowing from the bus controller to the RT. Okay, so now we have, if you remember the different message types that we discussed before, there was BC to RT, RT to BC, and broadcast. And using these two fields, we now understand how we can instantiate that. BC to RT as opposed to RT to BC is based on the value of the TR bit, and broadcast as opposed to non-broadcast is based on the RT address, whether it's a 31 or some other number. Okay, what we haven't yet talked about in terms of the message types are the mode codes. So that's next. And that's done by looking at the next field, which is the subaddress field. So the subaddress field has a number of different uses, one of which is that there might be complex RTs. In other words, in RT, let's say a radar. So from the communication point of view, it might be a single RT, but there might actually be multiple radars attached to that single RT or multiple modes within the radar. And each one of them has its own data to send, and therefore it'll get its own message. And the way we distinguish between a message from the phase array radar to a message to the whatever other kind of radar it is by using a different subaddress. And we have, since there are 5 bits here, we have the potential for 32 different subaddresses. Now, 2 of those subaddresses are special, 0 and 31. and some planes will use 0, and some planes will use 31, and some might say either, that if you use that mode code, then we're talking about a mode code. Then you use that subaddress, we're talking about a mode code, not a standard message. Right, so subaddress has two different uses then. One is to determine if this is a mode message as opposed to a regular message. That's done by seeing if the address is 0 or 31. And the second is to say within an RT, what kind of data do I want from that RT? It might be from a different subsystem, might just be different data. And that way, if there's a lot of data that a particular subsystem has, the bus controller can ask for data subaddress 7 or data subaddress 9 or whatever subaddress he wants. Okay, so that's the third of the 4 fields. And the final field is the word count. The word count is again 5 bits, and that's where we came for the design goal of up to 32 words of data per message. So again, 5 bits gives us 32 potential values. If you're reading the binary, so the values are going to be from 0 to 31. But in fact, if we're not talking about a mode code, we're talking about a standard message, then there's no such thing as a 0-word message. So it's really from 1 to 32. So what they did was they said, well, if you see a 0 in this field, interpret that as a desire for 32 words. Now, in terms of mode codes come in 2 flavors, no data words and 1 data word. So obviously I don't need a 5-bit word count to distinguish between 0 and 1. I only need one of those bits. And it turns out that that's exactly what they use, is one of those bits, and is bit 4. And as the high bit of the word count is used to determine whether the mode code is going to contain data or not. And the low 4 bits, which gives us 16 possibilities, are 16 different kinds of mode codes. So there are 16 kinds of mode codes with no data and 16 kinds of mode codes with data. And not all of them are even used, but there are a bunch of them that are used. I mentioned one before, there's synchronize. And in fact, synchronize comes in 2 flavors. There's synchronize with data and synchronize without data. Synchronize without data presumably means reset your internal time tag. Synchronize with data is set your time tag to the value of this word that I'm giving you. Okay, so that is the first word of every message. And now we understand how the bus controller, in fact, has control over the bus, because he sends this, yeah.
Somebody's asking, what do you mean by mode codes? I think they want a little more.
Okay, so a mode code is a housekeeping kind of a message. It's not designed to send data to an RT. It's designed to do things that are necessary in order to keep the bus running in a healthy way. So for example, there's a mode code that says don't use bus B. And normally it's up to the individual, no, it's not. It's up to the bus controller, as with everything else, which bus to use. But he can tell a particular RT that your bus is noisy. Every time you send something to me over bus B, I got a problem with it. So I just want you to shut down your bus B. Right? So this has to do with the health of the bus. It doesn't have anything to do with the actual communications that's going on. Another mode, so a mode code is a message intended to create a healthy environment for the bus. And we'll see other uses for the mode code later on. Okay, so we said that there are 3 kinds of words that go on over 1553 bus: the command word, which we just discussed, and then there's data and the status word. So I'm not going to talk that much about data simply because it's not defined in the spec. It's whatever information needs to be passed back and forth. There is a thing called a MIL-STD-1553 handbook, which is not part of the spec, but which gives guidance as to the kind of data that you might want to put over the bus. And for example, it says that if you want to give an angle, so angles are given in semicircles. This is as opposed to, I believe CAN bus uses radians, and 420, A-ring 429 uses degrees and minutes. So 1553 uses semicircles. That's, again, it's not part of the spec. So the spec itself says nothing. But the handbook says you might use 16 words of data for some things, 32 words for other things. All that kind of stuff is not part of the spec. And in any event, that's all stuff that when you actually have a project, so whatever RT that you're involved with is going to have to publish a book of exactly what data it expects to get in and what data it expects to send out, what the formats are. So here I'm going to discuss, instead of the data, I'm going to talk about the status word. The status word is sent by the RT in response to almost every message. So after the command word goes out, a status word has to come back, not necessarily immediately. Okay, so now we see here also 5 fields. There are actually more. I skipped a few because you'll notice that the bits don't add up to 16. So the first, let's go through them now one at a time, actually. So the first field is the RT address field, and the RT address field is a copy of the RT address field in the command word. And this is the RT's way of letting the bus controller know that he got the command okay. Now, potentially, there are always the possibility of errors on a bus. There might be noise, yeah.
A question, is it broadcast transmit message possible?
No. It's a good question. Broadcast can only be BC to RT for the simple reason that if it was RT to BC, you would have multiple RTs attempting to transmit simultaneously, which is not allowed on a bus. The messages would crash into each other and would be not understandable. So broadcast is always going to be BC to RT. And that way all the RTs get the message simultaneously, but there's only really one message physically on the bus. Now, let's say, for argument's sake, that the bus controller wanted to transmit something to RT2. And because of noise on the bus, by the time it actually got onto the bus, it came out as a 3, not as a 2. Now, this doesn't happen very often for 2 reasons. First of all, just because it doesn't happen very often, because the buses are shielded, so there shouldn't be too much noise. And second of all, because if a single bit would ever get changed, there would be a parity error. And I'll go into detail what that means exactly later. But the point is that the RT would know about it and would immediately throw out the command. Any command that has an error, the RT will throw out immediately and not respond to. But there is a small but existing possibility that there will be 2 errors in a word. And if there are 2 errors in a word, then let's say, for example, the parity bit changes and the low bit changes. So instead of an RT2 in the RT address field, it now contains a 3 and there's no error in the word. Okay, well, even this very slight chance is one that we don't want to take. And therefore, the RT responds with its own address in this field. So if the BC intended to go to RT2, but it actually went to RT3, RT3 is going to respond with an RT address of 3. The bus controller is going to see this and he's going to say, wait a minute, that's not who I had in mind. And then he's going to know that there was a problem with that message, and he has the choice of resending it or just ignoring the data. He definitely doesn't want to use the data because it came from the wrong RT. Okay, so now ordinary, so that's the reason that the status bit has to be set. And usually it's the only bit that's set. Everything else here is a special purpose bit. So the next bit that I wrote here is the message error bit. And the message error bit is an RT's way of saying that there was a problem with the previous command. In fact, it will not generally respond with the message error bit for the current command. There's when it gets a command word, if there's an error, usually it will not respond with a message error bit. The rules of 1553 is that for the most part, if an RT gets a command with a problem in it, it doesn't respond at all. However, the bus controller can send a mode code, and this is another example of a mode code, that asks what was the last command you got, or what was the last status that you would have sent if you had sent it. And if the bus controller sends that command, then the RT might respond with the message error bit set. Okay, now I'll move on to the next couple of fields. So service request is something we're actually going to speak about at length in the 1760 portion of the thing, but it is a mechanism for the RT to let the bus controller know that there's something going on that requires service. And I will explain later exactly what that means. The last two bits that I put down here is the broadcast receive. So as we said, a broadcast is not going to get an RT response for the same reason that you can't have a transmit broadcast, that if it did get an RT response, then all the RTs would respond simultaneously, and the bus controller wouldn't be able to hear it. Okay, so in that case, how does the bus controller know that the broadcast was received? And the answer is it can send the same get last command or last status, and then to a particular RT, and then that RT will respond, and if the previous command was a broadcast, then this bit will be set. And that way the bus controller knows that the previous command was a broadcast.
Dave?
Yeah.
I have one more question here. Regarding broadcast to all sub addresses in a single RT possible?
No. Within a broadcast message, there is a particular subaddress in the command.
Okay, thank you.
Okay. Okay, and the final bit is a busy bit. So the busy bit, it will commonly be used, or commonly it will not be used, but when it is used, then it'll most likely be on startup, right? Some RTs take a while to start up because they have to do a lot of self-tests and things like that. And in that case, if the bus controller asks them for data before they're completely ready and haven't done their self-tests yet, then they don't have any data to send. So this bit gives them a way to tell the bus controller, ask me again later. I'm just not up to it right now. And it's discouraged by the spec. Discouraged means to make your things start faster, or at least have default data in it so that even before you completely start it up, this default data will be somewhat meaningful. Okay, so now we've discussed on the bit and word level what goes on over the bus. What is a command word, what is a data word, and what is a status word. And now we'll put them all together into a message sequence. And so this is what you're going to see if you're looking at the bus, and we'll actually look at it in an oscilloscope view soon. But this is more of a conceptual view. So now we said the two most common messages are a BC to RT message and an RT to BC message. And this is what they look like in terms of word order. So BC to RT message starts with a receive command, meaning that the TR bit is equal to 0. It goes out to a particular RT or broadcast. So let's say, for argument's sake, this particular receive command is going to RT2, TR bit is 0, the subaddress is a 1, so it's not a mode code, and the word count is 7. So following this receive command, I expect to see 7 data words, right? And these 3 dots here just indicate some random number. And in our case, altogether, there are going to be 7 words. So these 3 dots are going to be 4 words, and the 1, 2, 4, and 1 is 7. And they're going to be contiguous, right? So on the bus, there's no space between the words. You can see where one word starts and another ends. And we'll get to that when we discuss physically what the bits look like. But right, in terms of the command, so you have the command word, contiguous to the command word, 7 data words. Then you've got this star here. right? This star represents a response time. And the response time means the bus controller has just finished his transmission. Now it's the receiver's turn. And all the receiver has to, means the RT's turn. And all we expect from the RT is a status word. And the status word is there to let the bus controller know that he got it. He got the command and he got the data. And if there are errors in any of those things, then the status word will not be sent. Now, there are some exemptions. If there is an error in the data, then it's a choice given by the spec whether you want to send the status word or suppress the status word. But the simplest case is where the status word is not going to get sent. And therefore, the response time is very important because it's a window. The bus controller at some point has to know to give up, that he's never getting a response. Otherwise, he's going to waste too much time waiting for it. And therefore, the spec says, and this is an order of magnitude of about 10 microseconds, that the status word is supposed to be sent back. And if the bus controller doesn't see a status word in the course of, let's say, 14 microseconds, then he's going to give up, and he's now allowed to send the next command. Now, this dot here represents the intermessage gap time. We've just completed an entire message, and we're now ready for the next message. And so the time in between those messages is called the intermessage gap time. And there's a minimum of like 2 microseconds. There's no maximum. And as if I don't happen to have any rush to send anything, then I can just not send. The bus controller can just decide to have some quiet. And in fact, good practice is when you develop a new bus, you don't really want to use more than 50% of the time available to you, because in another month, somebody's going to come up with another message that he'd like. And if you filled it up to start with, you've got no room to grow. So you're really best off not filling it more than halfway. And then you've got space over the course of potentially years before you actually fill up the slots. Now, if you do fill up, then you're up close to 100% throughput. So then you've got a problem. If somebody wants to add something, what do you do? And there are a number of options. One option is split it into 2 buses, right? This is not simple to do, both in terms of the wiring and in terms of the logic, because the 2 buses can't easily talk to each other. In fact, they can't do it at all over the 1553 bus. The same bus controller or the same mission computer might act as a bus controller to both of them, and then it can play games. So obviously that's complicated, and you want to avoid splitting things into multiple buses if you can. But that's one of your options. There are a few others. Anyway, I want to go down to the transmit command. So the transmit command will again have as the first field the RT that's supposed to transmit, followed by the TR bit being set to 1, followed by whatever subaddress you want, followed by the number of data words that the RT is supposed to transmit. And that's it. That's all the bus controller now has to send is the single command word. And therefore, following the command word, we immediately are waiting for the response time. So now, again, we've got on the order of 10 microseconds to respond. And the first word that the RT responds with is the status word. Following the status word and contiguous to the status word are however many data words were requested by the bus controller. So those, yeah.
Another question was asked if Excalibur cards supports less than 4 microseconds response time.
It's actually not legal to have less than 4 microseconds response time, and we do not. In fact, depending on the message types and things, we're usually closer to 7 or 8 microseconds. And in fact, most of the RTs I've seen are also very few people get to the minimum, because what the processing that the RT has to do once it gets the command word, first of all, can't even start processing until the command word is completely finished, because it has to know if there's a parity error. If there's a parity error, it's not allowed to do anything. And then after that, it has to figure out if this is, first of all, if this is him, right? First, it has to see, is it a legal command word altogether? Once it's a legal command word, he has to look at the RT address and see, does this RT address refer to him? If it does, he has to look at the TR bit and decide what he's supposed to do about it. He's supposed to get the data, or is he supposed to send the data? Then he has to look at the subaddress to determine which data. If he's sending, where is he getting the data from? And if he's receiving, where is he sending the data to? And then he has to get the data and start the transmission. That all takes time. And 7-8 microseconds is not bad. Okay, so now the two that we saw before are the most common things that you're going to see on a bus: BC to RT messages, RT to BC messages. Just for sake of being complete, I'll talk about the RT to RT message. RT to RT message, the bus controller sends not one command, but two commands. The first command he sends is to whichever RT is supposed to get the data. The second one is to the RT that's supposed to transmit the data. After these two commands both go out, then there's a response time wait, and then the transmitter starts to transmit. And he transmits, like every transmitter, starting with the status word and then followed by the data word. Meanwhile, the receiver RT, who knows that it's a RT to RT command, because after he got his command, he saw that what happened next was another command. So he waits for this data. And when the data is completed, then the receiver will respond with his status word. What's interesting, by the way, here is that, as I just said, the receiver knows it's an RT to RT command. The transmitter does not. Because when the transmitter got the receive command up here, first thing he did was look at the RT address and see that it wasn't him. So he threw it out, and now he's waiting for the next command. Well, the next command came right here, and it's for him. But he doesn't remember that there was another command there. So as far as he's concerned, this is a standard transmit command, and he does what he would do if it were a regular transmit command directly from the bus controller. He sends the status and the data. The RT does have to know, because it's unusual for the RT to, there's this whole, normally the RT status is going to come after a command word and all the data. And here it's not. It's after two commands word and status and the data. Remember, this status word does not contain a subaddress or a word count. He had to get that from here. So the RT has to, after he gets this command, he has to know to ignore this command, ignore the status word, and just take the data. Now the last kind of messages are mode commands, and because mode commands contain either no data words or one data word, it turns out that there are three kinds of mode commands. So one kind is the kind that has no data, and it's comprised completely of two words: the mode command itself that the bus controller sent, and the status response that the RT sends. Now, if you have a broadcast mode command, you don't even have the status, and the entire message is going to be a single word. And then you've got two kinds of mode commands with data, depending in which direction the data is going. So if it's an RT to BC mode command, then the bus controller will send the command, and the RT will send the status and a single data word. And if it's a BC to RT, then the bus controller will send the command and the data word, and the RT will then respond. Now, in the case of the command with no data, is it a receive command or is it a transmit command? And the truth is that it's neither, because there's no data, so there's nothing being received or transmitted, but the TR bit does need a value. Turns out that for no particular reason, they chose to have the TR bit set to 1 on mode commands without data. Okay, so that's pretty much all there is to know about what a message looks like on 1553. I'm going to discuss for a couple of minutes what MIL Standard 1760 adds to it. Now, MIL Standard 1760 is designed for missiles. In fact, it's designed particularly for nuclear-tipped missiles. So they looked at 1553 and they said, we got to add a few things. So some of the things they added have nothing to do with communication. They have to do with discretes, with missiles, as opposed to most other parts of an airplane are not designed to come back with the plane. So they need to be connected to communication wires at some point, and then at some point they need to be not connected to communication wires, right? Once you send them off the plane, you'd rather they left the wire behind. So that's part of the 1760 spec, but not the part that I'm interested in. The part that I'm interested in has to do with the messages themselves and slight changes that they made to the messages, or additions that they made to the messages. And there are three flavors of changes that were made. They added checksums, which means that the last data word of some messages is a checksum of all the previous data words. So that's a safety check that there were no errors. We mentioned before that there's a parity check, and a parity check can tell you if there was a single bit error, but it can't tell you if there's a double bit error. Checksums are much more sophisticated, and they can tell you for pretty much any number of errors. And you can imagine why, in the case of a nuclear-tipped missile, you really would want to decrease your chances of error even more than usual. SRQ processing, I had promised to discuss, and we will do that shortly. And then there's a thing called a header word. So we'll get to them now one at a time. A checksum is a fairly complex, it's actually not a checksum, it's actually a CRC, cyclical redundancy check, which is more complex than a checksum. And it is a way, an algorithm that you put each data word that comes in into the algorithm. And after you finish with the last data word, it gives you a value. And that value should be the last data word that comes in. And if it isn't, then you throw out the message. Now, not every message needs one. Messages like blow up that town, you would want to have a checksum on. Messages like, how are you feeling today? You know, is your status okay? Are you feeling healthy? That it's important, but it's not important enough to warrant the checksum. So it's not on every single message. The bus controller will decide each time it sends a message whether he wants to have a checksum attached to it. For RT to BC messages, the decision is made by the RT, and it's usually based on particular subaddresses. Now, on our cards, at least, in monitor mode, we always figure out the checksum, and we set a bit in the status where it's telling you whether that there is a valid checksum in the last data word or not. Now, as opposed to most other bits and status words, this is not an error condition. It's up to the user to decide whether it's an error or not, because if there was no checksum expected, then the fact that the checksum didn't match is not an error. If there was one expected and it doesn't match, that is an error, and it's the application who's likely to know whether he was expecting a checksum or not. Okay, SRQ processing. You'll recall that in the status word that the RT sends, there is a thing called an SRQ bit. Now, what's that for? So let's say you are an engine, right? And the bus controller periodically sends messages to the engine, right? Such as, I don't know, how much thrust I need, how much power to output. And once in a while, it asks questions of the engine, such as how much fuel have you got left? But there are special circumstances which hardly ever happen, like engine catching fire, for example, which the bus controller is not going to ask, because since it happens, once every 30 flights, it's a tremendous waste of throughput resources to ask it constantly, are you on fire or not? On the other hand, we do want the bus controller to know about it as fast as possible. And yet, all messages are initiated by the bus controller. So the RT can't just send a message to the bus controller saying, I'm on fire. There's no way he has to do that. So they needed a mechanism to, on the one hand, not take away the power of the bus controller to be in charge of every single message, but on the other hand, to give the RT some method of letting the bus controller know that there's something going on here that he needs to know about. And the method that they used was this SRQ processing. So that, for example, let's say the engine is on fire. And there's a lot of data that the engine can send regarding this fire, and that data is all in subaddress 3. But subaddress 3 is something that the bus controller never asks for because he doesn't anticipate a fire. However, he does ask for subaddress 5, which is the fuel level. He asks for that periodically. He also periodically sends things to subaddress 2 to tell the engine to produce more thrust, or whatever it is that pilots want to tell engines. Okay, so now what happens is that when the bus controller sends a message to either subaddress 2 or subaddress 5, which it does periodically, the RT now has an opportunity via the status word that he's going to send back anyway to inform the bus controller that something's going on that he needs to know about. And that's the SRQ bit. So the RT now lights the SRQ bit when he transmits the status word back to the bus controller. And the bus controller now knows there's something wrong. Now, something wrong isn't good enough. He needs the additional information that's going to tell him what's wrong. And therefore, what he'll do immediately upon getting this SRQ bit is he's going to send another mode command that we haven't yet discussed called a send vector. A send vector mode command. And the send vector mode command is a command that has a single data word that comes from the RT to the bus controller. So as soon as he sees the SRQ bit set, the next command he's going to send out is this send vector mode command. And this send vector mode command, in the case of 1760, has two options. One of them is if the high bit is a 0, then it means that it's a status word. And the status is something which the bus controller presumably will understand. And the other possibility is that the transmit command, that the vector command is actually tells the bus controller the subaddress and the number of data words that it should be asking for. It doesn't need the RT number because the status word is coming from the engine, so the bus controller knows it's the engine that he needs to talk to. But he does need to know which subaddress contains the data of the problem. Now the RT knows that it's subaddress 3 because he knows that the problem is a fire, right? It could be 4 other problems that have data in other subaddresses. The RT knows that it's the fire, so he's now telling the bus controller, listen, the problem here has information for you in subaddress 3, and there are 7 words of information. The bus controller then sends the next command, which is to the RT number of the engine, to subaddress 3, asking for 7 data words, and it's a transmit command. And then he'll get the data. And now he'll know what's on fire, how hot it is, how far is it spread, whatever information it is that is available about the fire. So this SRQ is a very powerful mechanism for allowing the RT to give surprise information to the bus controller. And really, we could have done this by just having the bus controller once a second ask, are you on fire? But given the number of possible things that could go wrong and all the different RTs, this is a much better mechanism because this is a mechanism that costs 0 time if nothing goes wrong and doesn't cost a lot of time if something does go wrong. So it's much, much more efficient than just polling for problems. Okay, the third thing that 1760 added, which again is a safety check, is header word checking, in which the first word of a message, and it can be a BC to RT message or an RTB message, but the first word of the message is defined by the 1760 spec. And therefore, if, for example, subaddress 11 is supposed to have a data word 410 in front of it, and we'll see in a minute what the actual values are, and it doesn't, then if it's an RT to BC message, the bus controller will look at the first data word and say this is wrong and throw it out. Or an RT to BC message, the RT, or BC to RT rather, the RT will see that the first data word is wrong and he'll throw it out. And these are the values that are written in the spec. Subaddress 1 needs to have a 420 transmit, right? Which means that if the RT is asked to transmit data for subaddress 1, the first data word must be a hex 421, and so on with the other messages. And this is just another check to make sure that the right RT got it and he did it correctly and he knows what he's doing. Okay, well, I hope the people are there. The limited feedback makes it hard to know. Okay, anyway, moving on to session 3. These are things which some of them are in the spec, some of them are not. But they're very important to know when writing actual applications and designing RTs and bus controllers. So they primarily have to do with timing. We're going to talk about major frames and minor frames, and also give a few examples, which also show some more use of mode codes to give an idea of how real-life needs translate into communications. So in terms of the timing issues, the 4 things we'll talk about is intermessage gap time, response time, which we actually saw already, major frames and minor frames. Now the intermessage gap time is the time between messages. The rule is that it must be at least 4 microseconds as measured from, it actually should be mid-parity to mid-sync, which we'll see what that actually means a little later. It also means it's the same as saying 2 microseconds of dead time on a bus. It's just easy to measure mid-sync to mid-parity. Now, there is no maximum, and as I said before, when you start designing a system, you really want to use not more than half of the available time. So whatever time you're not using is going to be spent in intermessage gap times, right? You've got messages take less than 50% of the time, then the time between messages takes more than 50% of the time. So that the spec does give you the minimum and no maximum. Now, occasionally we have people asking us if we can handle intermessage gap times of a second or 10 seconds or things. In fact, we've done it. Our original implementation only allowed up to a certain number of milliseconds because it's really unreasonable to have more than that. And usually when people ask us to do things like that, one of us doesn't understand what's going on because there are various problems that can be solved in different ways. We typically prefer customers to discuss with us what their problems are rather than to tell us how to implement the special case for their solutions, because we might be able to help. We have enough experience with this kind of thing that if we understand the problem, we might think of a different way of solving it that might work better. So that's one of the things that I like to stress to customers. I really like it when people talk to us and discuss problems so that we can come together and discuss solutions. In fact, another thing that I've been mentioning in these Zoom courses, now that it's so easy for us to talk, is that if you're in early stages of a project and you have to make design decisions about what kind of bus to use and what kinds of RTs to use and things like that, we're happy to be involved in that. It does us, I mean, it'll help you because we have a lot of experience that we can share, and it helps us because the more we understand about the actual uses that our customers are making of the buses that we support, the better we can make our products to help out in supporting those uses. Okay, response time, we saw what it is. Response time is the amount of time that the RT has to respond following either a transmit command or a receive message, including the data. Now, the original spec of 1553A put it at 7 microseconds. 1553B expanded that to 12 microseconds. Now, that doesn't mean that after 12 microseconds, the bus controller automatically gives up, because there's a certain latency on the bus, right? Even if it takes time, not a lot of time, but certainly tens of nanoseconds of time, maybe hundreds, for the command word to get from the bus controller to the RT. Now, the RT's time doesn't start when the bus controller transmits the command word. It starts when the RT gets the command word. And then he has his 12 microseconds. But then when he sends his status word, it takes time till it gets to the bus controller. So that adds another potentially hundreds of microseconds. So the bus controller wants to allow more than 12. Typically, they'll allow like 14, 15 microseconds. Another thing that could affect the response time is, we'll see later, there's a thing called a bus repeater. And a bus repeater extends the length of a bus, but it does take extra time. And so even if the RT is really fast enough and it's responding in the 11.5 microseconds, by the time it goes through a bus repeater, it could go up to 12.5, 13 microseconds, and therefore the bus controller wants to wait a little more time. Now, in our cards, we allow the bus controller to set what we call the response time window before it gives up. Okay, a major frame, which we have seen from our things the customers have shown us, is typically between 20 and 80 milliseconds. And it represents all the messages that are going to go out. Now, you really want a bus controller to be straightforward as much as possible. Theoretically, you could design a bus controller that every cycle is going to be different based on real-time events. And people have done it. But it's complicated and prone to error. So what you're really better off doing is having one frame that contains all the data that you need, and just sending that frame over and over and over again. Now, and that's what a major frame really is. Now, occasionally there might be exceptions. There's a thing called an asynchronous message, right? So that could happen if some event, not on the bus, but some event that the mission computer, which happens to be the bus controller, is privy to, sees, maybe on a different bus, who knows, and he'll decide that there's some urgent message that has to be sent right now. So that's called an asynchronous message. That's an exception. But if there's an exception, that means that there's a rule. And the rule is that the same messages get sent out all the time. So that's what we'd call a major frame. And a major frame can have the same message more than once, because it seems unlikely that every message is going to have the same urgency as every other message. So how do we deal with that? Right? Some messages just are, you can call them high priority, and another way of putting it is that they're more time critical. So for example, knowing your altitude is something you certainly want to know, but the likelihood is that if you only find it once a second, you'll be doing fine, right? Because it doesn't change that fast. And if it does change that fast, the pilot is well aware of it without his instruments telling him. So that's important information, but it's not time-critical information. Whereas your radar telling you that there's a heat-seeking missile heading for your tail, that's time-critical. You want that now. So let's say we have a simple example of a bus in which you've got 3 different messages, A, B, and C. And A is this heat-seeking missile, and C is the altitude, and B is, I don't know, engine heat, which I arbitrarily decided is somewhere in between those two in time criticality. So what we're going to do is we're going to have a subframe. Our major frame is 40 milliseconds. And the major frame looks like AC, AB, AB. That's what a major frame is. And every major frame looks the same as every other major frame. But if we go drill down into the minor frames. So there are 4 minor frames within this 40 millisecond major frame. Each of the minor frames is, of course, 10 milliseconds. They're all the same size. And what I've done is I put A in every single one of them because it's time critical. So I don't want more than 10 milliseconds to pass before I find out if I've got a heat-seeking missile heading towards me. On the other hand, 40 milliseconds is plenty of time to know my altitude, and the engine 20 milliseconds is fine with me also. And this way, I get more time critical messages more often, but I don't have to fill up my entire throughput of the bus by asking for every message that often. So more time critical go more often, the less time critical will go less often. Okay, now let's talk about some things that you might expect to see in an aircraft and what does this mean in terms of 1553 communication. So here's an example that a pilot, the fighter pilot is going on his merry way and he's about to head across a border of a country that doesn't necessarily want him there. So he wants to know that his armaments are working. So we'll talk about a single missile that he's interested in knowing. What's its status? Is it happy? So he wants to tell the missile somehow to execute a self-test. The missile has to generate the self-test, and we need this data in a place where the pilot can see it. Heads-up display sounds like a good idea. Okay, so that's the function that we want to perform. How do we perform it? So the first thing that you got to understand is who are the RTs involved, right? So there are 3 different RTs involved. One of them is the button that the pilot pushes that has a little sticker on it that says Test Missile 2. So that button we'll call RT2. The missile itself is also an RT, and he's the guy who's got to do his own self-test and tell us how he's doing. And the heads-up display is the 3rd RT in our little scenario. So, okay, so now what messages do I need in my frame in order for this to work? Okay, well, the first thing, what I really want to know is, did the pilot push the button? So periodically, I got to send a message to the button, right? The bus controller asks the button, were you pushed? That's a transmit message, and you really only need 1 bit in that particular message. So we'll send a word, and bit 7 is going to be the bit that says 1 means pushed, 0 means not pushed. So that's that message has to be on the bus list. Now we have the next message is going to be the bus controller is going to send a message to the missile saying perform your self-test, right? And it's going to be based on that bit. Now here you have an example where if I want to be clever, I will not send this message in every bus frame because why should I send it if nobody hit the button? Alternatively, if I don't want to be clever, but I want to have a simple system that works, I will always send a message to the missile, but the data in the message will be the data that I got from the button. There'll be a data bit that says perform a self-test, or if it's a 0, it'll say don't perform a self-test. Now, you don't really need to send the message not to perform a self-test. If you didn't send the message, it would also not perform the self-test. But for simplicity's sake, and to know what your bus list is and to know how much time you need under all circumstances, it's a lot simpler if it's in there. Okay, so now having sent this message, a little while later, I'm gonna get back, and here inter-message gap time might be important, right? Because it takes time for the missile to perform the self-test. So I can't tell it to perform it and then immediately ask for the data, because if it takes it 20 milliseconds to get the data, it's not gonna be ready yet. So I have 2 choices. I can wait 20 milliseconds before I send it, or I can use those 20 milliseconds to send 17 other messages because I've got the rest of the plane to deal with too. That's certainly reasonable and legitimate. But at some point, I am going to ask the missile for the data, and that's going to be an RT to BC message from RT3. And then finally, the BC now has the self-test information from the missile, and he's got to transmit it to the heads-up display. So this whole mechanism of pilot hitting the button and then seeing what's on the display turns out to require 4 separate messages, and the timing is also important on the messages. So this is all something that the system architect has to think about. Okay, another example of something you might want to do is synchronize all of your terminals, right? You've got an inertial navigation system, you've got a GPS, you've got the engines and the radar, and you'd like them all to kind of work together. So you want to make sure that all of them know what time it is. They know they have the same time tag running. So you'd like to make sure that you'd like to make it happen, and then you want to check that it in fact happened as you asked. So in terms of RTs, we've got a lot of RTs, right? All of whom I want to synchronize. In order to synchronize them, I want to send a single broadcast message to all of them, telling them now is the time to synchronize, because they all get that message simultaneously. So it's a good method for synchronizing. And then afterwards, I want to check with each one, or at least with the ones that are most critical to me, did you in fact get my synchronize command? And the way I find that out is by sending a mode command called send last command. And what I'll get back from this is right. So the command it's actually an RT to BC command. I have to send one at a time. I ask each one of the RT to send the last command. So the bus controller asks for the last command, and the RT responds with 2 words. One is a copy of the last command word, which should be the broadcast command. And the next is the status, which says, did the broadcast command come okay? And by checking each, potentially up to 31 different RTs, I now know whether they're all synchronized or not. Okay, so that handles the non-directly spec-related issues. And I want to talk about how you connect the bus, because we had a lot of experience with people connecting it incorrectly, and it's a very, very, very difficult problem to solve, because things will sometimes work and sometimes not, which are the worst kind of problems. I want to talk about differential signals and bus termination. So I'll see what each of these things mean. Now 1553 bit encoding. So now I'm at the bit level, and the question is how, and this is one of the major questions that every bus has to answer, right? So there are really 2. I decided that there are 2 major issues for every communications bus to resolve. One is, how do you make sure that multiple transmitters don't transmit simultaneously? And the second is, how do you distinguish between a 1 and a 0? So the way that 1553 distinguishes between a 1 and a 0 is something called a Manchester code. Now, the signal of the code moves between plus and minus 3.75 volts, so 3 3/4 volts. And in the middle of every bit, it crosses 0. And as it either moves from plus 0.375 to minus 3.75, or it moves from minus 3.75 to plus 3.75. So it's always moving in one direction or the other in the middle of every bit. And the direction determines whether it's a 0 or a 1. Every data bit is 1 microsecond, and a parity bit is also a microsecond. Parity bit is not technically a data bit because it's there just to show that the data is correct, but it doesn't really contain useful information to the user. In fact, the user doesn't even see it. The user will get a status telling it whether the parity was correct or not. And now there's this thing called the sync, which I haven't talked about till now because it's really only relevant when you get to the really lowest level of the communication. And the sync is a way of distinguishing between command words and data words. And the sync is 3 microseconds, and therefore the middle is at 1.5. And there, again, it always either goes from +375 to minus, or from minus to plus. One direction is a command word, the other direction is a data word. And I'm very carefully not saying that up is command and down is data, because, as we'll see in a moment, that can be misleading. Okay, so now what does this look like? So let's look at a picture of 2 bits. The first bit is a 1, and in this case, I say it's going down. And that's partially true, and we'll see when I talk about differential signals why I'm hedging. But you see here, the bit time itself goes from this 0 to this 1, right? That's a single bit time, that's 1 microsecond. The middle of that, in a half microsecond, in this particular instance, you see that the signal is heading down. That makes it a 1. In this case, it's heading up. That makes it a 0. Now let's say I wanted 2 1s in a row. How would I do that? I need this to be going down in the middle. So the way I would do that is by, in between bits, I would send it up, and then I would now be able to go down in the middle and onwards. So the middle of each bit always is changing direction. Between bits, sometimes will change direction, right? So generally speaking, if you have the same bit value twice in a row, then it's going to have to change direction both in the middle and in between. And if you have different values, then it won't. Okay, so that's the way you can distinguish between a 1 and a 0. And so that was just, you know, a simple table in Word, I think, was used to create that. But if you want to know what it really looks like, if you're looking on an oscilloscope, so we'll see in a second, and we'll see it looks quite similar, actually. And over time, the hardware has changed. It used to be trapezoidal, meaning that the up wasn't up at a 90 degree, it was up like a trapezoid at some angle. And eventually they moved to sinusoidal, meaning that there are no sharp turns at all. And sinusoidal turns out to be a much cleaner signal. So this is what it looks like. And so now we see that a 1553 word, in fact, is 20 microseconds long. Every word is 20 microseconds long. And those 20 microseconds are comprised of 3 fields. The first field, look on the bottom, is the sync, which is 3 microseconds long. Following the sync, you always have 16 microseconds of whether it's command status or data. Those 16 are what the user sees. The user doesn't directly see the sync, and he doesn't directly see the parity, which is the final bit. What the user cares about is the 16 bits in between. So when we talked about the RT address and the subaddress and the RT, but all of that, that's all in those 16 bits. So the sync in this case is going down. The parity looks like it's going up, as does most of the data. And you see in here an area in which we changed. I can't tell you offhand if we changed from a 0 to a 1 or a 1 to a 0, but this is what a change looks like. When you don't have a change, we saw that it has to go up in between bits and in mid-bit, whereas here, this is a mid-bit, but in between the bits, it didn't have to change. Okay, so that's what a single 1553 word looks like. Command words, status word, data words, all are of the same format, but the direction is going to be a little different. So here, this one is going down. That's telling me that it's a command word. Now here is an example of an entire message. So 3 words, each one of which is 20 microseconds. The first word, now by looking at it, I know that it's a BC to RT command. How do I know? Because I see that these 2 words are contiguous. Whereas here, there is a response time. So, so this, therefore, in addition to which I see that here, the sync is going down, and here it's going up. Okay, so that means these are different syncs. If they're different syncs, then this has got to be a command, and the second one has to be data, because you're never going to have it in the opposite order. Commands are often followed by data. Data is never followed by a command. And in fact, data is never even followed by a status, because if an RT is sending both status and data, the status is going to go first, not last. Okay, so therefore, here's a command sync. And I can't tell by looking at it that it's a receive command from the bits, because the TR bit is hidden somewhere in here. If I looked at it carefully, I could tell you. But I don't need to see the TR bit, because just the fact that it's got a data word contiguous to it tells me that the bus controller is the one who's sending the data, and therefore it's a receive command. Okay, so this is what a BC to RT looks like. And RT to BC, you tell by virtue of the fact that the data is not attached to the command, but rather is attached to the status. And here you see that in the command word, the sync is going down, and in the status word, the response is also going down, because status and command sync are the same. And the data is the opposite, where it's going up. Okay, so now I'll tell you why this goes to why I was hedging about the down and the up, because the pictures that we looked at till now, in which command sync was always going down, is only one of the two wires that are used in 1553. Because it's a differential signal. A differential signal always has two wires. That's kind of what it means. And the first one is the one that we saw, and the second one looks the opposite of the first one. Actually, oh, that's a shame. I had put in another slide showing more what it was, but okay, so now if we go back to here, so what that means is that the complement, let's say I have it over here, so the dead is the same, but here, whereas the top signal went up, the bottom signal is going to go down, right? And then it's going to go up in the middle and then down, so it's going to be exactly the mirror image of this. Therefore, if the sync is heading down in the first wire, it's going to be heading up in the second wire. So it's not really fair to say that sync going down is a command sync. It's more correct to say that sync going down on A as opposed to A prime is a command sync. On A prime, it has to be going the other way. And the same is true of the data. It's always the opposite. Now, what's the advantage of having two different wires that are complementary? And the main advantage is that, that 1553 is a twisted shielded pair. It means these two wires are surrounded by copper. Now, this does a couple of things for us. The first thing is that if I want to know if the signal is high or low, so if I only had one wire, then high and low would be relative to ground. Only airplanes aren't on the ground. So ground is not quite as well defined. It turns out that ground on one box may not be the same as ground on another box. And therefore, there's room for confusion. However, here, if this signal is high, in other words, it's at plus 3.75, then the mirror image is going to be at minus 3.75, which means that the gap between them are 7.5 volts. On the other hand, and as the gap, assuming that I'm this minus this. On the other hand, if I look at this signal, so this is minus 375 and the other one is plus 375, the gap between them is going to be the reverse. So just by looking at the gaps, and not relative to ground, just relative to themselves, I see, are these signals far apart or are they right next to each other? And that tells me, without reference to ground, whether I'm looking at a high signal or a low signal. The second advantage is coming from the shielding, that if there's noise, right, passing through a lightning storm, or somebody's playing with their iPhone navigator, so that if that causes noise, then the noise will affect both signals the same way. because they're shielded. And therefore, any spikes will be a spike on both of them, which won't affect the distance between the two signals. And therefore, I'm kind of impervious to noise. So those are the two advantages, that I'm not dependent on ground and spikes won't bother me. Okay. And then the next thing I want to talk about is bus termination, right? What happens here is I have a signal going out of my RT, and it goes from my RT through my stub onto the bus. From the bus, it goes all the way in both directions, right, to the right and to the left out of that stub, along the bus. And at some point, it hits the end of the bus. Now, before that point, it hit the bus controller, and the bus controller is trying to read the data. But it doesn't stop there because it doesn't know which point is the bus controller. So it goes till the end. Now, when it hits the end, what is it supposed to do? It turns out that electrons, and that's really what the signal is electrons moving through the wire. They like moving through wire, right? That's called conductivity. Copper is an excellent conductor of electricity. And therefore, conductor means that the electron is happy to move through it. And you can think of it as water moving through a pipe. But what happens when you get to the end of the pipe? So in water, if the end of the pipe is open, then the water flows out. And if it's closed, then the water crashes back. Now, if you're watering your lawn, you want it to be flowing out. If you're not, you prefer not. In the case of an electron in communication, you want it gone, because it's already done its job in terms of sending the data to the bus controller. But if it hits air in this case, air is a very bad conductor of electricity. And therefore, it's got a choice now, right? The electron has just come to the end of the wire, and it says, all right, if I go forward, I'm going to be in air. If I go backwards, I'm going to stay on copper. Let's go backwards. And that's what it's going to do. And that's going to cause reflections. And reflections are interpreted as noise. So we want to avoid that. And the way we avoid that is by putting a terminator on the bus. And what a terminator does is it makes the electron think that the bus is continuing. But once it gets into it, it can't escape. It's kind of like the Bates Motel. And therefore, it's not going to go back onto the bus. So here is a picture of the topology of a bus, in which I've represented the ends of the bus as A is one end, and A prime is the other end. And these are the ends where we're going to put terminators, right? Because when RT2 wants to send something to the bus controller, so its electrons are going down to here, and they're going to go both ways, left and right. RT1 is going to ignore it, and the BC is going to pay attention to it, and then it's going to go to A prime, and we want it to stop. We don't want it to come back on the bus. So the terminators do that, which is why it's so important to put terminators on your bus, because otherwise they'll generate noise. And the problem with noise is that it sometimes causes parity errors, it sometimes causes other errors, and it sometimes does not. So you may get away with it for a while, and then all of a sudden stop. So we've had cases where people haven't wired things exactly the way they should, and they work perfectly well. And RT2 has been transmitting to the BC perfectly fine for weeks. And then they added RT7, which has nothing to do with RT2, and nevertheless, it caused RT2 to stop working, because it meant that the length of the bus was different, which meant that the reflections were slightly different, and they messed things up. So sometimes things that appear to have no relationship to anything can mess up the data if you don't do things properly. Okay, so A and A prime you need terminators for. And now, what about B? B, and there are 4 Bs here, and each of them represent how we connect a box, either an RT or a BC, or a monitor could be, to the bus. How does this connection work? Okay, so it turns out that's called coupling. And these junctions have to be coupled to the bus. And there are two methods that the spec mentions for how to couple, how to connect your box to the bus. And they're called direct coupling and transformer coupling. Direct coupling basically means you just attach your wire to the bus. In fact, you can pretty much skip the bus altogether if you want to just attach the two boxes to each other. This turns out not to be a very clean method of doing it, but for lab use, point to point, you can do it, and the spec says only do it if the things are right next to each other. The maximum length of the stub should be not more than a foot. And then the way you connect is just kind of wrapping the wires. So that'll work for simple cases, but a much cleaner way of doing it is by using a transformer coupling. This is an example of one that we happen to sell. It's called a box coupler, and it's for use in a lab. And it does all kinds of filtering. There's electronics inside it, which makes the signal come out clean. Now, one of the important things to mention here is, it might be a little difficult to read, but the two connectors on the sides, all right, this guy and this guy. So if you look at the writing on the box itself, here it says bus J2. Here it says bus J1. Whereas here, these three guys are called stub J3, stub J4, and stub J5. Now they look the same. And so you can connect your 1553 cable, which is a twin-X connector. In theory, you could connect it from here to any of these 5 connectors. Physically, you could, but you shouldn't. This has to be connected to a stub. The bus controller connects to a stub. An RT connects to a stub. Monitors connect to a stub. So what connects to a bus? The only thing that connects to a bus is the bus, which is to say a wire. Why would I want a wire here? Because this has a 3-stub coupler, and I'm going to put it in the part of my lab where I've got 3 of my RTs. And then I might have my bus controller and another RT on the other side of the lab. So what I'm going to do is I'm going to run a wire from here to the other side of the lab. On that side, I'm going to stick it into a coupler just like this. And then that coupler is going to have an output for the bus controller and a second output for the RT that's on the other side of the lab. So now I've got a 1 wire connecting this coupler to that coupler, and I've got 5 boxes attached. And then I've got the other side, right? So let's say this side has the wire attached to the other, then this side, I want to put the terminator on. Similarly, the other coupler is going to have the bus attached to it on one side, and the other side, I'm going to put another terminator on, and then I'm going to have a clean signal. If you use a coupler, you're allowed to have 20 feet between your bus controller or RT and the coupler. And it's a very clean signal. Now this is a picture of a inline coupler. Functionally, it's exactly the same. Again, you've got 2 wires which represent the bus, and 3 wires which represent the stub. So in that respect, it's exactly the same as the picture on the previous page. They come in many different configurations. All right, couplers can come with 1 stub, 2 stub, 5 stub, 10 stub, any number of stubs. And some couplers come with built-in terminators, especially the ones that are going to go on aircraft. This inline is meant for use in an aircraft. And the advantage over the box is that they're smaller and weigh less, and in some cases are better made. I believe in our case, we make them both well. Okay, direct coupling should not be used on an aircraft. It's for use in a lab. And even we, in fact, don't use it in a lab either, possibly because we make the couplers so we have them available. But we don't encourage it in any case. Okay, so now I mentioned before briefly a repeater, and why would one be interested in a repeater? So there's a thing called a repeater and a splitter, and what they're for is special circumstances. Namely, the spec says, we just mentioned that you're allowed to have 20 feet between a stub and a device. In other words, the stub is on the bus. So between the bus and the device, you're allowed to have 20 feet. The entire bus from end to end, right? The two ends have the two terminators. So from one terminator to the other is not allowed to be more than 300 feet. Now, if you're talking about and the original design, remember, was for fighter planes. Fighter planes are not that big. 300 feet was more than sufficient for the needs. However, times change, and now there are many reasons why 300 feet may not be enough. One might be because you're talking about a tanker, which is based on a full-size aircraft, and those are very big. And remember, it's not a question of 300 feet from end to end of the plane, because the bus is going to be winding and wrapping around things, right? It can go from the cockpit, then you may need it to go all the way to the end of the wing, and then back to the end of the next wing, and then back to the fuselage and to the end of the plane. That's already easily could exceed 100 meters. In addition, 1553 is not only used on aircraft. We've seen more and more uses of 1553 on naval ships. And ships are very large. It can multiple stories tall, as well as very large from, I think it's bow to aft, but I don't really know. So for various reasons, 300 feet may not be enough. Okay, but you need 500 feet. And yet the spec says don't do that. So now the question is, why does the spec say not to do that? And the answer is because signals tend to degrade over time and space. And the signal in 1553, they assumed that by the time it goes 300 feet, it's already sufficiently degraded that we don't trust it anymore. Well, up till 300 we trust it. 301, we don't trust it. Now, obviously, there's no real difference between 300 and 301. But spec has to give you a number, so that's the number. So what you can do is that at the end of the 300 feet, you can put in a box which will take the signal, and instead of just sending it on, and which means it'll get even more degraded, it recreates the signal so that it now looks like new. And in that case, you've got another 300 feet of clean signal. That's what a bus repeater does. These pictures on the bottom are examples of the one on the, they both are bus repeaters. The difference between them is that the one on the left doesn't handle the kind of environment that the one on the right does. The one on the right handles the kind of environment that you get on an aircraft with vibrations and differences in air pressure and heat and all kinds of other things. So depending on the particular needs, one will be more appropriate than the other. So with those, you can extend a bus from 300 feet to 600 feet, and you can extend a stub from 20 feet to 40 feet. Now, a splitter is it's actually similar hardware, but it's a completely different function. Let's say you've designed your aircraft, and when you design their aircraft, one of the more complex parts of it is the harness. Right? The harness is all the wires that are necessary in the aircraft, and there are thousands of them. And so once you install them, it's not something that's easily taken apart. For one thing, they're behind the walls. And you really don't want to mess with them more than you have to. So when you first design it, you have to know where all of your couplers are going to be and leave some place to access the, right? So the harness is behind the walls, but it's got to come into the aircraft to allow you to have these stubs that can connect to your RTs. So you planned this all wonderfully well, and you've got your harnessing, and you've got your stubs and your couplers, and then somebody dreams up a new need for a new device, and you don't have place for it. So you don't really want to rewire the entire aircraft. That's extremely expensive and going to cause all kinds of trouble. So if there was a way to turn a stub into a bus. So now instead of a stub is only, you're allowed to stick a single RT into it. But if I could somehow alter the signal so that it looks like it's a bus, then I can stick a bunch of RTs onto it, and I could attach it instead of just having one stub out, I can attach it now to a coupler and have 5 stubs coming out of it. I'm still going to be restricted to overall not more than 32 boxes. But if I've only got 10 boxes, then I can add 5 in this particular spot. So that's called a bus splitter. And it allows you to add RTs where you hadn't expected to without messing with the harness. Here's a picture. Yeah.
A couple of things been asked if the repeater requires a separate power.
Yes, it does.
And
yeah, because you're creating a new signal, so that's an active job. That's not just passing something along, but creating a new one, and therefore it'll have usually like a 5-volt input.
All right, and the other thing was, well, you're up to it now. But they're interested in dual redundancy and bus monitors.
Okay, excellent. So we've come to the right slide. In fact, I don't know if you're aware that I was told this by a professor once that there are no bad questions. There are good questions and very good questions and excellent questions. And well, skipping to the excellent questions is a question that the next slide answers. So here we've got a picture of a bus. Now I've got here a whole bunch of different devices that might be on it, and I've called them device 1, device 2. You can have any other number of devices in device N. And here, this will be my test computer. So let's say, for argument's sake, that the test computer is the bus controller. These 2 guys are RTs, and the top is a monitor. Right? In terms of connection to a bus, there's no difference between a bus controller, a remote terminal, and a monitor. All of them have to have 2 connections, which we'll call bus A and bus B. That's the dual redundancy. And the bus A connection is going to go into a coupler, which is attached to bus A. This is the bus. It starts here with a terminator, goes through a coupler, through a bus wire, through another coupler, another bus wire, another coupler, and a terminator. And that's all bus A. Bus B is parallel to this. It doesn't have to look exactly the same. Right? So here you see I've got a 2-stub coupler, 1 stub I'm not using. And whereas here it's only a 1-stub coupler. Here I've got the 2 of these RTs are both on bus B on the same coupler, but on bus A they're on different couplers. These are things that don't matter. They probably won't happen. I would guess that most designers are going to say bus A and bus B should be exactly parallel. But according to the spec, there's nothing that requires that. So if it's convenient, you don't have to. But, so the important things to see here are that bus A is going to 1 active bus. Bus B is going to a second one. Both buses at the ends have these terminators, top and bottom. You're allowed to have empty stubs. Sometimes people put smaller terminators, like 3 ohms as opposed to 70, which is the terminator at the top. We found that to be less critical. Right, and that's yeah. So that's what the topography of a bus actually looks like on an actual aircraft. Now, whether this is a bus coupler or an inline coupler will depend on your circumstances. In flight, you're more likely to want to have an inline coupler, mostly because of the weight and the space, both of which are at a premium on military planes. Okay, and there's a plug for Chaim. Most of the things we've discussed, plus quite a few other things, are available on our website or by talking to Chaim. Okay, and this is, we have our regular website, as you know, is MIL-1553.com, which can lead you to our secondary website, 1553couplers.com, which focuses on cables and couplers and terminators and all kinds of other splitters, I guess, too. Okay, now a final word on something which there's been a lot of interest in recently, which is a translator. Very often what you'll have is that you've been used to using a particular military bus or any kind of bus, and you've got to change for some reason or other. Now, we've had this, for example, on helicopters. Right, so a helicopter, if it's a civilian helicopter, it's very likely to have a lot of Airing 429. If it's a military helicopter, it's very likely to have a lot of MIL-STD 1553. But what will happen, okay, since there's a lot of parallelism, all right, the things that you need to fly a military helicopter and things you need to fly a civilian helicopter are pretty much the same. Right, the same aerodynamic principles, the same kind of rotors, so there's a lot of similarity there. So it can easily happen, and it has happened, that you've got this plane, which say was designed around 1553, and one of the boxes on the plane, let's say inertial navigation system, goes obsolete. These things happen, and now you've got to replace it. Now it turns out not to be easy to replace it because the box of the inertial navigation system was fit exactly into a particular place on the helicopter. Which means that your new box better fit into the same place. So it has to be the same fit. You'd prefer that it not be heavier. You'd prefer that it not take up not take more power. You prefer that it not be hotter. So you've got a lot of preferences here, some of which you can flex on, some of which you can't. And let's say you found, and of course, you want functionality. So let's say you found one, and you found something and it fits gorgeous, and it's half the power of the other one, and it really does everything you want it to do plus, but it's not 1553, right? There's a lot of inertial navigation systems out there. Some of them work on Airing 429, some of them work on Ethernet, some of them work on serial, and this thing is just perfect, except that it doesn't speak 1553. So, up until a few years ago, your basic option was to not use it because it's true that it's perfect in every other respect, but every other respect isn't good enough. And so you had to keep on looking, and maybe you would have had to compromise on the weight or on the power consumption or on the heat or whatever. Today, we introduced the Mac, which allows you not to compromise. What the Mac does is it takes this inertial navigation system, let's say speaks Ethernet. It then gets the Ethernet message from the from the INS. It's smart enough to know to take apart the message and say, okay, what's in this message? It's got altitude and longitude and latitude and whatever else it's got. And then act as an RT, sending the same data under the appropriate subaddresses and the appropriate type of data. For instance, it might get an angle in degrees from 429. In 1553, it's expected in semicircles. So the Mac handles all of that. So at the low level, instead of using 429 bits types, which is non-return to zero, it uses Manchester for 1553. It knows the structure of a 1553 message as opposed to the structure of a 429 label. It knows and it will change the data type from degrees to semicircles. So now you can use this box, which does everything else perfectly, and you don't have to worry about the different languages because we do the translation. And we can translate between 1553 and 429 or 708 and 825. Hu9 turned out to be a predecessor of 1553, which is still in use in certain F-15s. And the Mac would be an ideal way to, it's not in wide use. It turns out that it's in fact very limited use. And a lot of these planes have an entire Hu9 bus for a single device. Well, obviously it would be more convenient to use the 1553 bus controller that is already connected to a dozen other devices and just make this one more. The Mac lets you do something like Okay, so that takes care of the hardware part of the course, and now we'll talk about different things that you can do with software. And we're constantly developing new software at Excalibur. And I'll talk about a few different things that we have in terms of what kind of problems do they solve. So the first thing I want to talk about is who are our customers? And again, I enjoy it when our customers talk to us and tell us what they do and what they need, because it lets me make up slides like this. It also helps me know what I'm doing. So one of our kinds of customers is a system integrator. That'll be somebody like Airbus or Boeing or Lockheed that makes planes. And they don't make all the parts of the planes. They actually make very few of the parts of the planes. They'll buy the engine from Pratt & Whitney or Rolls-Royce. They'll buy the landing gear from whoever it is that makes landing gear. They'll buy radars from one of a whole bunch of different companies. They'll buy the screens from somebody else. And they've got to make all of these things work together. So that's a systems integration task. On the other hand, we've got the RT developers. So General Electric, Pratt & Whitney, Rolls-Royce all make engines. Rafael in Israel makes missiles. Astronautics makes monitors. Elbit makes heads-up displays. So all of these guys, what they have in common is that they're focused on one particular subset of the plane. They don't care about the rest of it. They're not integrators. They don't care about mission computers. They care about their particular niche. Okay, so those are the kinds of customers. Then you've got, what are they trying to do? So in the early stages, it's very often problem isolation, right? Things don't quite work. In the case of systems integration, they don't work together. In the case of RT development, it's just not finished with the development yet, and we got to find out what works and what doesn't. So that's problem isolation. And then you've got this more in the integrators side of things. It's done. You've finished your integration. You're ready to fly. And now you want to make sure that the flight went well. You want to review things. You want to see, did anything go wrong? Even if it went right, did it go right in the most efficient way possible? Is there room for tweaking systems? Okay, so what is the nature of systems integrators? So let's say you're Boeing and you're developing the 797. So you've got the brand new engine and a brand new bunch of radars and brand new, who knows what other things. A lot of stuff is new, and you parceled it out to a bunch of different subcontractors who themselves parceled subparts of their RT to other contractors. And they some of the stuff has been delivered and some of the stuff has not. So you need to simulate whatever hasn't been delivered yet. So that might include the bus controller. It might include 10 of the 20 RTs that are on this bus. So you want the ones that are real, you would like them to think that there's an entire rest of the plane out there. But there really isn't. So you have to simulate all those other things. In addition to simulating all of the other parts of the plane when they work, you want to also simulate what happens if they don't work. All right, let's say you're testing a display, and the display will sometimes get errors, even from perfectly good RTs because of noise on the bus. You want to make sure that when it gets those errors, it handles them properly. You don't want it to give you bad data when it gets an error. You don't want it to freeze up when it gets an error. You want to make sure that it handles it. Maybe it'll tell you that it got an error. Maybe it'll just not tell you anything, but it won't put up stupid data. But you got to check what it does in the case of errors. And you may want to monitor, you want to make sure let's say the bus controller came in and not necessarily all the RTs. So the bus controller is responsible for efficient use of resources. So you can monitor everything it's putting out, check the data that it's giving to the various RTs, check the timing, make sure that it's not trying to stuff 3 seconds worth of communication in a second. because it's not going to work. So this monitor can tell you all of that. Okay, and because of this, I'm going to list some of our products. So Merlin, for example, is a free software package that we give out, and it allows you to simulate bus controller or multiple RTs, or bus controller and multiple RTs. So it can do, and it can inject errors. It can do all of these things, and it can tell you the timing. It doesn't tell you much about the data, right? So it's more useful for just seeing that the communications is working. If you need to know what data or simulate data, it's not the best tool. But like if you're developing a monitor, say, so the first thing you got to check is that the communications work before you worry about the actual data. So here, this is a screen from monitor showing a BC concurrent RT. Means we're simulating both the bus controller and some of the RTs. Now there's a different screen that tells you which RTs we simulate, but this screen tells you which messages are being sent. And of course, being sent, the most important thing to know in terms of the message is the command word. And that's what we have here. This column shows you the command word. In case there's an RT to RT command, there are two command words, so you'll have the second column, command word 2. And we just parsed it for you. So it turns out that a 1081 is a BC to RT command because the 6th bit from the left is a 0, so the TR bit is a 0. And it's got a single data word. It's got the 1 is the low thing. And it's RT to subaddress 4, which you'll have to take my word for it. Okay, so here you've got all the messages that we want to send, BC to RT, an RT to BC, a mode command, and an RT to RT. So these are the 4 basic types of messages. And we've decided to inject errors. In the case of a BC to RT, we injected a word count error. So even though it says it's only supposed to send 1 word, maybe we'll send 3. In this case, RT to RT command, and we injected a parity error into the command word. And now, using this, you can see, is your RT able to handle these various types of errors? Is it able to ignore messages to other RTs, right? If it's, for instance, RT6, then I expect it to only see message 4, because it's the only one to RT6. Very important thing to check. And I can adjust the frame time and the intermessage time. Here you see there are 150 microseconds between this message and the next. These are things that I can adjust to see, can the RT handle the stress? Okay, another thing we might want to do for problem isolation, for example, let's say I had a flight and I was monitoring, or I want to monitor on the flight. In order to see if there were problems, and if there were problems, I want to reproduce those problems in the lab. So how do I do that? So in the picture, we have what we call a Lance, which is as you can see, a handheld 1553 monitor. And it will, you can bring it with you on the plane, plug it into any available stub, and it will record everything that goes on that bus. Now, you get the pilot is going to tell you when he gets off the plane, listen, 22 minutes in, there was a red light on one of my RTs, and you know, you got to find out what it is. Is it serious? Is it not serious? It happened. Okay, so now what we do is we take the data off of this device and we run it through a program called the data reconstructor, which retransmits all of the messages that had been transmitted previously on the bus. Now, if the red light went on a particular, whatever the red light was attached to, that RT, so I'm going to attach my data reconstructor to that RT. I'll simulate everything other than that RT. And as far as that RT is concerned, it's seeing exactly the same thing that it saw on the aircraft, which gives me a fairly good chance that that you're going to see the red light in the lab. Now, of course, if the red light was caused by a cold air current in the plane, you're not going to see it. But if it was caused by anything that came from any of the other boxes on the aircraft, then you are going to see it, because the communication that it saw on the plane is identical to the communication that it's going to be seeing in the lab. So in addition, so you can certainly use this for isolating problems. In addition, if you have a flight and you see how everybody responds to the flight, then if you make a change, this is a good way of testing if the change you made messed anything up, right? Retransmit the entire flight again and see that everybody behaves the same way, other than what you wanted the change to accomplish. Okay, another use for software in 1553 will be a post-flight analysis. And as you had the flight, I'm not looking for errors here. I don't need to reproduce anything here, but I do need to understand the data. Now, for this, Merlin isn't going to help, because Merlin doesn't understand much about what the data is. It's more involved in the timing and sequence of the messages at the message level, not at the data level. Whereas Exalt deals more at the data level. So that, first thing it'll tell you, actually Merlin will do this too, were there errors? Were there communication errors? So if I see that at the end of the flight, RT7 had 400 communication errors, all of them on bus A, then I know that I have to look at the attachment to bus A. Maybe it's a cable that was attached to bus A, maybe it's the connector, but there's something wrong there, and I know I have to look for it. So having the error statistics on a per RT and even a per subaddress level helps me isolate some kinds of problems. Then I can also look at data patterns, and so I can see what was the altitude at every point of the flight from the beginning to the end. I can get a graph that shows me exactly what was going on. I can get another graph that tells me what the engine temperature was. And I can get a third graph which compares engine temperature to altitude. We once actually had a case in which a client was having trouble with his communications and didn't understand why, so he asked for our help. It turned out that every time his plane went above 20,000 feet, it stopped working, just because some parts were freezing. And the only way to see that is to look at the data and to notice that at the time, and look at all the other data at the time that the error occurred. And if you consistently see that the altitude is above 20,000 feet, that tells you something. So it gives you a direction for what it is that you need to fix. Okay, so that's what Exalt is very good at. And here's a picture of the Exalt main screen. What you can see here on the left, what we call the access board, is that you can have on the same software a whole bunch of different types of communication. So you've got, you can have Ethernet, you can have Hu9, 1553, 429, all of them working simultaneously. Now our boards handle all of these simultaneously because our boards are modular and we have modules for each type of communication. And here you've got the same software can also handle it. So in this case, I can get the oil pressure off of 1553, whereas I'm getting the altitude off of Hu9. Now this is a made-up example. I don't think there are any planes that get altitude off of Hu9, but that's not really so much the point. The point is that even if you've got on your plane a mix of different types of communication, you can see all of them in one place. And that does happen. Certainly on military planes, you're going to be seeing serial and Ethernet in addition to 1553. On civilian planes, AFDX, CAN bus, and A-Ring 429 are really designed to work together, right? Because if you have a sensor that gives very little data, you really don't want to attach AFDX to that. That's CAN bus or A-Ring is much more appropriate. On the other hand, if you've got the sensor on the end of a wingtip, you don't want to run a CAN bus from the end of a 380 all the way to the cockpit. It's not designed for that kind of length. So you really want to get the data on the CAN bus and then transfer it to a AFDX. And the AFDX will run an Ethernet wire to the cockpit, which is certainly capable of doing. So therefore, the idea of having multiple data sources on an aircraft is not at all unusual. And that's one of the many things that Exalt is designed to handle. It also, you see here, there's a range and an alarm. And what that does, it says airspeed, for example, and airspeed is given in knots. However, I also tell it I want my airspeed to be between whatever my minimum is and whatever my maximum is. And if it's not, then I want something to pop up in red. And that way I see at a glance where my problems are. So here you have as an example, altitude, and I decided that my altitude shouldn't go above, say, 15,000 feet. Here it's 20,000 feet, and it's red, right? Because I previously defined it as that 20,000 feet is too high. And I can see it either, this gives me the current altitude, and if I want to see altitude over time, then I use a time graph for that. So there are multiple ways of displaying data. Okay, I think we're done for today. I thank you all very much. If you've got any questions for me now, feel free to ask. If you think of any later, email is good.
We have a question here. I'm sorry, I don't particularly understand it. Maybe the person asking the question will ask it. It's regarding our 1553 coupler. Regarding cable adapters, there are T-types and L-types of cable adapters. Is it just a passive splitter?
The T-types are passive splitters, yes. Now, when you put we do that sometimes if we want to attach a device to a coupler, but we also want to attach an oscilloscope. So you have an adapter that looks like a T. So it's the bottom part of the T screws into the coupler, and then the two sides, one of them you can put your RT and the other one you can put your oscilloscope. And that would be passive. It's just basically a wire.
Okay, I hope that answers your question. Again, thank you, David, for your presentation. If anybody has any questions, please feel free to send me an email. We have these slides available on PDF, and we'd be happy to send it to you. If we can be of any help in the future with any of your projects, please feel free to contact us. And once again, thank you very much. And we hope to see you soon. Have a nice day. Have a good day.